Okay, let's continue on what we talked about last time. Let me share my screen. Okay. So for the in-tube heat transfer, we talked about the flow and the heat transfer, right? Give you a quick review, okay, here. Flow and important because we always concerned about the frictional loss. So we need to calculate the shear force, the drag force, right? There's one equation you probably need to remember. I think in the fluids class, some of you already took, you already know this is the equation for calculating the loss, okay? You need to know how to convert the loss into, the head loss into pressure drop, then convert the pressure drop into drag force, shear force, okay, listed on this note, okay? So very important to understand that. And in order to calculate the head loss, you need to find this coefficient F, right? So Moody diagram, I sent you the picture for the Moody diagram on GroupMe last time, right? So you need to know how to use it. In order to use the Moody diagram to find your F value, you need to calculate the Reynolds number, okay? Reynolds number, important. Then you should be able to find the friction coefficient, then the drag force, frictional force, important, okay? Oh, by the way, I think I didn't mention the laminar or turbulent, right? That share the same equation, but in the Moody diagram, you see, you notice there's a straight line for the laminar flow friction coefficient. F equals to what, 64 over Reynolds number? Is that right? Is Reynolds number over 60 or 64 over Reynolds number? I think is, let me check the diagram. Yep, it's 64 over Reynolds number. Okay, for if it's laminar flow, basically you don't even need the Moody diagram. Basically, they have an analytical solution. Okay, this. You might also have a question, say, hey, how do I know this flow is laminar or turbulent? Okay, anybody? In flat plate, boundary layer will also know how to determine its laminar or turbulent, right? How about the tube flow, pipe flow? Educated guess, anybody? By looking at which number?
Is it the Reynolds number still?
Absolutely. You want to look at the Reynolds number, okay? So in the boundary layer flat plate, the critical Reynolds number is what? Do you remember?
Is it 5 times 10 to the 5th?
That's right. Okay, that's a critical Reynolds number, separate laminar and the turbulent flow for the boundary layer. Okay, now in here is this Reynolds number is less than 2000 for the pipe. I put a D here, Reynolds number D, that means diameter, right? So if it's less than 2000, we consider it's laminar. Okay. So if the Reynolds number is greater than 3000, we consider it's turbulent. Okay. They're good. So it's really different numbers. You know, in the flat plate, it's in the millions, right? The Reynolds number. So here in the Reynolds number is in the only thousands. Okay. So what about in between? In between is not good. It's called transition region. Okay, it's bad. It's so complicated. It's not fully turbulent and it's not fully laminar. So you're doomed in that region. There are not much equations you can use. Okay, people don't have a much of the certain information knowledge if the pipe flow is between this Reynolds number range. Okay, so what's your strategy then as an engineer? If you work on designing a pipe, okay, your strategy is try to avoid this range. Okay, so either make it laminar or make it turbulent. Okay, so in that region, if you have to be in that region, maybe you need to do some experiment yourself to do the measurement to determine what's the characteristic of that. Okay, does that make sense? Okay, so 3,000, 2,000, 2,000. Okay, that's a rule of thumb, laminar and turbulent. Okay, so last time we did the flow side, right? Flow side for laminar, we even have the analytical solution for the velocity profile, right? For turbulent is even easier. So it's just like uniform velocity for turbulent pipe flow. Although the velocity is chaotic, fluctuates all the time, but it fluctuates about a mean value. So it's okay for our practical engineering purpose to take the average value, okay? It doesn't see much of the wall effect in turbulent pipe flow. In laminar, you see the wall effect. So the velocity profile becomes parabolic, okay? But in turbulence, it seems like there's very few wall effect. So it seems like it's a mean velocity occupies the entire pipe. So which is good for us, right? Calculation-wise, it's much easier. We don't need to worry about the expression used in the laminar, okay? We started to talk about the heat transfer characteristic of the pipe flow. First of all, we talk about the laminar heat transfer equations. We give a velocity profile, right, for the laminar pipe. I'm sorry, not velocity profile, temperature profile for the laminar flow. Depending on the center temperature, you should be able to calculate temperature any place inside the pipe, okay? It's only a function of radius. So any location, you should have a radius to the center, right? Distance to the center of the pipe, which is the lowercase r here, okay? So then you should be able to calculate the temperature. We also introduced the bulk temperature. Actually, the bulk temperature is used a lot in the industry application. It's the average temperature, basically, okay? We determine that heat transfer coefficient for the laminar pipe flow is 48/11 K/D, okay? Then the Nusselt number, the dimensionless heat transfer coefficient is even easier. It's a constant, okay? But be aware this is for the iso heat flux condition, iso heat flux. So it's a constant heat flux on the pipe wall, okay? But I think 95% of the application you see in industry is iso heat flux, okay? Usually it's really, really difficult to keep a constant temperature on the wall. So usually you can keep the constant heat flux, which is the power input, okay? So in addition to the laminar, which indeed has a equation for the Nusselt number for the isotemperature, isothermal condition, okay? Laminar pipe flow isothermal, okay? So the equation is, actually there are two equations, 6.9 and 6.10, but I don't want to give you 6.9. It's in the textbook, okay? I just don't want to use that because it's more complicated form, okay? I like the equation 6.10. I think equation 6.10 is a little bit better than equation 6.9, okay? Nusselt number, now you know it's average, okay? In isothermal pipe flow, pipe heat transfer, the Nusselt number is not a constant along the pipe. Remember previously in the iso heat flux condition, since you have the same heat flux everywhere, basically the same Q, right, input into the system everywhere. So with the temperature linearly increase, the Nusselt number is almost constant everywhere with iso heat flux. But with isothermal condition, the Nusselt number changes, okay, along the flow. So I give you an average Nusselt number equation, okay, which is for the entire pipe, which is good. Average Nusselt number times average temperature difference, then you can calculate the total heat transfer, right? 1.86 times Reynolds number. Here, the Reynolds, I'm going to talk about the all Reynolds number D. Okay, I just don't want to write that D. You know it. It's not the flat plate. Prandtl number to the power of 1/3 D over L times 1/3. Okay. Then they are the viscosity ratio. Okay. To the power of 0.14. Okay. Bear with my writing. It's a question in the textbook. Okay. Here, one thing is new here to you is the viscosity ratio. You consider, so sometimes in some of situation, if the water temperature is much higher than the fluid temperature, the property, you have to take into account the property change between the near wall region, which is high temperature, to the middle of pipe region, which is low temperature. The property could differs, okay, although the same fluid, because the temperature difference. So mu is the temperature, the viscosity at the bulk temperature, or at the, let's say, in the center of the pipe, the flow temperature, okay. And the mu W is the viscosity of that fluid when it's at the wall temperature, which could be much higher or much lower, okay. So most of the time, this ratio is close to 1, okay. If the temperature difference is not that great, it's close to 1, right? But if there's a significant temperature difference, this equation can account for that,
Dr.
okay.
Zhang,
Yes.
what is the exponent on that mu ratio?
It's 0.14.
Okay.
Okay. Okay, so that's the new equation I like to introduce. But there is a limitation for this equation, okay? It can only be applied for this condition. Condition is Reynolds number times Prandtl number times D over L greater than 10. Okay, so for the isothermal condition, I only have one equation for you, okay? But that equation only work for that range, for this greater than 10 range, okay? But most of the time it should, okay? It should work. But check it in case it's not, right? Most of the time Reynolds number is in the thousands, okay? Prandtl number is about 1. So if the D over D is not that different, okay? I'm sorry, D over D is not that small, so it can work.
A quick question, Dr. Zhang.
Sure.
What page is this formula on again?
It is on page 283 to 284. Okay, so the pipe flow, follow my lectures. The book has a different arrangement talking about the pipe flow heat transfer. Part of it is in chapter 5, part of it is in chapter 6. It sometimes confuse readers, okay? So I put them together. I concluded, summarize it for you. So that's why it can be here and there, okay? So this is the laminar equation. So we have 2 equations, right? For laminar heat transfer, laminar pipe flow heat transfer with isoheat flux and isothermal, okay? So you should be able to handle, but sometimes in this type of problem, let's look at the example. In this type of problem, you need to consider the properties. At what temperature you receive the property. It will be always, that's why I ask you to do that Excel project. Because in the future, when you encounter real-time problems, most of the time you're gonna do iteration, because the property changes a lot when you apply with different temperatures for the fluid, okay? It could be. So let's look at example 6.2. It is a laminar tube flow and the heat transfer, heating of water in laminar tube flow, okay? So let's look at this example. I think we can finish this example today, then we leave turbulence next week, turbulent pipe flow next week. Or maybe if we have time, we can still introduce the equations. Okay, water at 60 degrees enters a tube of 1 inch, 2.54 centimeter diameter. Okay, so the diameter is 2.54 centimeter. The temperature in is 60 degrees Celsius. Okay. At mean flow velocity 2 centimeter per second. Okay, your velocity V, let's say U. Okay, I said last time if I have a particular problem, if it's 1D, I use letter U. Okay, 2 centimeter per second. Okay, calculate the exit water temperature if the tube is 3 meters long. Okay, now I think I need to introduce another equation. I think you learned it. That's not me introducing. You probably learned it in thermodynamics class. So we want to calculate the T at the outlet. Okay, do you remember the energy equation you use to calculate the energy difference for a pipe in and out?
Mass times the mass going in times the enthalpy going in equals the mass going out times the enthalpy going out.
I think it is that equation, but I like to use the other form. Let's say the Q, energy change, let's say delta E. Okay, let's say delta E, how about that? It's actually the heat transfer, right? We receive heat from the wall, right? And let me see, what's the wall temperature? Did it give? Water temperature is 80 degrees, okay. T wall is 80 degrees C. Okay, so you receive heat from the wall, right? Your fluid temperature is 60, enter the pipe. So water is heated at 80 degrees. So the energy, you will gain energy, right? For this fluid that flows through this pipe. Is that right? Okay, the total energy gain will be equals to those energy transfer from the side, from the wall. Okay, but the total energy gain, we can use this equation, right? Mass flow rate times Cp. Do you remember this? T out minus T in. Is that right? Is this equation, does that look familiar to you? Did you use this equation before?
A lot.
Yeah, a lot, right? In thermal, right? In thermodynamics, right? Yeah, so that's good. There's a lot that I assume you everybody understand. So then in our heat transfer, we can replace this delta E by what?
Q.
Yeah, by Q. You're good now. Okay, energy balance, right? That's the total energy gain. It's our total heat transfer into the fluid from the pipe. Okay, so I guess when you look at this equation, is your unknown in this equation? What is your goal for this problem?
Find T out.
Find T out. T out is in my equation, okay? So that's good. I'm happy because now I put down the equation. I know it is the correct direction, although maybe I still need to go over many things to calculate the TO, but at least the TO is in the equation, okay? Let's see what we have. TI we have, I check it. CP we should, okay, later I'm show you what temperature we use to find the CP, but we should be able to have CP. Okay, do I know M dot? Do I have the diameter of the pipe? I think I have a diameter here, okay. Okay, I think I need to put down the length too. Length is 3 meters. Okay, so do you know how to calculate the mass flow rate, M dot?
Take the cross-sectional area, multiply it by the velocity, and multiply that by the density.
Bingo, you got it. Okay, good. I know everything, huh? Property, don't worry about that. I should be able to find property. Okay, now, in order to calculate the TO, so what do you need? I think my task here is to find my total Q, heat transfer going into the paper, okay? Okay, so what is the equation for Q? Anybody? All right, the equation here. I'm waiting.
Would it be HA delta T?
Yeah, don't be confident, right? Don't hesitate. Okay, that's correct. But I need to write a little bit in detail for this. So H, I know we're gonna leave it later, right? H, we should be able to find with our knowledge now, we learned it today and yesterday. Okay, what is A you're talking about?
That's the surface area of the inside of the pipe.
Okay, anybody can give me an expression for the surface area? Use letters, don't use the number, okay? Anybody know how to calculate the surface area of a cylinder? Come on, this is middle school geometry.
Pi dl.
Yeah, okay. Pi what?
Pi dl.
Pi dl, that's absolutely correct, okay. Delta T, what is the delta T we're talking about? What delta T?
Is that the temperature from the wall to the bulk temperature?
I think probably you want to use, now you know you're gonna use the average Nusselt number, right? Average heat transfer curve, because this is a isothermal condition problem, right? I put the average H bar, right? Is that right? You're gonna use this equation on the same page here, okay? Nusselt number average. So you're gonna use average. Wall temperature is average already, right? It's not average, it's a constant wall temperature. So you probably need to have an average bulk temperature. Average, exactly, yeah, but you can just say the bulk temperature for the entire pipe. Okay, so actually this TO and the TI, inlet outlet, is already the bulk temperature on the inlet surface and the bulk temperature on the outlet surface. Okay, so how about the average? So how about the bulk temperature for the entire tube? How do we approximate it? Half, I put a half there. Can you see it? Can you see what I wrote? Everybody, it's very important. Fully understand what happens, what the temperature change inside the, I think for the pipe flow, the temperature change linearly inside. Okay, so that's why we can safely assume that average temperature is just average temperature of the in and out. Okay. Any question to this? Is that good? Do you feel comfortable with this assumption? Okay, we're doing an engineering application here, right? A lot of times it's not perfect analytical solution. You understand that, right? So we use our judgment to decide a best estimate, okay, for some of the value. Here, it's almost linearly changed. Temperature should be linearly changed, gradually increase, right? Inside the tube, inside the pipe. So it will be okay to use the average temperature of the in and out, to treat it as the average temperature of the entire Okay. Is that okay? So far, so good? Hey, 21 of you here. I just want you to learn everything I said in the class. So it can save you time to study after class. Okay, that's my point. Okay, I want all of you 100% understand the thing I wrote down for this problem right now so far. They're good?
Yes, sir.
Okay, let's proceed. Now, so this will be equal to this. Okay, my TO again appeared in this side of the equation. Okay, it's fine. We can combine these two as long as there's only one unknown, right? TI I still have, TO I have, D I have, L I have, pi I have. Okay, so only thing I need to figure out is what? The H bar, right? Okay, I have to write on the next page. So H bar equals what? Anybody? Nusselt number bar times D divided by K, or times K divided by D.
Times K divided by D.
Okay, times K divided by D. Okay, so I guess that's the procedure. Now I know my last step is to find out the K. Oh, I'm sorry, find out the Nusselt number with this equation, right? Isothermal condition. Okay, so I think that's the procedure. Now we need to undergo some detailed calculation, right? So for detailed calculation, we need to know the properties. Okay, that's always an important topic to find the properties. Okay, so what temperature? Okay, so now look at those are the detailed, tedious part, right? So let's look at the textbook. It uses fluid temperature first. Use fluid temperature at the inlet to estimate the property, not estimate, what should be the word? To determine the property, to find the property. Okay. Then you know probably it's going to do a second try. Okay, when you get a better temperatures, when you calculate the TO, then you can have a better temperature to represent the average temperature of the fluid to find a better property. Okay, so with this, I think you got the density, 985 kilogram per cubic meter, right? That's what we needed for calculating the mass flow rate. Okay, CP, we know we need that equation for the main equation, right? Energy equation, 4.18 kilojoule over kilogram per C. Okay, viscosity, sure. Viscosity is, let me see. Do I need to know two viscosity? I think I need to know two viscosity, right? 4.71. That's the viscosity, 4.71 times -4 kilogram meter. This is viscosity at the fluid temperature, 60. And the viscosity at the wall temperature will be 3.55 times 10 to the -4. Why you need the viscosity wall temperature? Because in this equation, you think you're going to use the viscosity ratio here. That's why you need the second viscosity, right? 80 degree and the 60 degree. These are the two temperatures. And then K is 6.651 watt meter Celsius. Okay. Then Prandtl number for this case, what is the Prandtl number? 3.02. Okay. So I think these are the property we needed for this problem. Okay, now notice you're gonna use this equation. That's your only equation. So you are going to check to see if this condition is satisfied. Okay, be careful. If I give you an exam or quiz, I need to see you check this requirement. Okay, if you don't check it, if you just directly use it, I need to take some points off. Okay, so let's check that condition to see if that equation is okay to use. Reynolds number times Prandtl number times D over L. Actually, for this problem, equals to 27.15 if you substitute all those properties in there. Okay, it's greater than 10. But before I do this, actually, you need to actually calculate the Reynolds number, right? What is the Reynolds number for this case? You need to make sure, although I haven't tell you much of the turbulent pipe flow equations, heat transfer equations yet, right? Obviously, this is a laminar flow, okay, because it says laminar flow. But you need to really check to see Reynolds number is greater than 2000 or not, or less than 2000, okay, to make sure it is laminar. 1062, okay? So it is less than 2000. See, you see the procedure here. It's very tedious procedure. You have to make sure you have like millions of equations to pick, right? You have to make sure all those conditions is right for you to pick one equation. Okay, good. So now it's safe to apply the average Nusselt number equations. Okay, for the isothermal condition. So the Nusselt number is 5.816. Okay, notice if it's iso heat flux condition, there's a constant Nusselt number. Do you remember what is that value? I don't think it's 5. It is what? I think it's 4 point something, right? 4.364. That's for isothermal. So this is iso. I'm sorry, that was for the iso heat flux. This is isothermal. Okay. The Nusselt number is not constant anymore. Okay, it is a value, but depending on the condition, you have equation to find the Nusselt number. Okay, therefore your H bar is 149.1 watt meter square C. Okay. Okay, now go back to the previous page. Okay, now we get H calculated. Okay, everything calculated here except the TO, right? Outlet temperature in this equation. M dot, M dot. We haven't calculated M dot yet. What is M dot? Row cross-sectional area. Be careful, this is not the surface area of the pipe. This is cross-sectional area of the pipe where the fluid goes through, okay? Times the velocity, okay? I think we have everything here. So the mass flow rate is 9.982 times 10 to the -3 kilogram per second. Okay, is that good? Now I have everything, so we can calculate the TO, outlet temperature. Do I have it in the textbook somewhere? Okay, 71.98, almost 72 degrees. Celsius. Okay, now I have a outlet temperature. Now I can do a better estimation for the properties. So your T, let's say it's not, we're not call it T film temperature anymore because film is only for the boundary layer. It is a film, right? So here it's a pipe. So average pipe temperature, how about that? So average temperature in the pipe, we can use half of the TI plus TO to estimate it. So it's around 66 degrees. So with that 66 degree, you are going to do the iteration now. Property again. Now, these are all the properties from based on the 60 degree. Now you're gonna have another set of property with 66 degree is better estimation here. Mu wall is still the same, right? Wall temperature is 80, okay? But you should have the rest of all the properties. With that, you check this again. I said step 1, step 2, step 3, step 4, step 5 is from the previous page, right? From the main equation to calculate the temperature. Then you go through 1, 2, 5 again. Usually the second round could be your final, because then in the third round, now what you calculate the TR is what? Let's say 71.88. That's close to the 71.98 from the last round. So if you do the one more round, it won't give you any difference, right? So your average temperature is still about 66 degree. Okay, maybe 65.94. Okay, so I think that's close enough, okay, to 66. You won't see any difference in the property. So it will turn out to be 71.88 degree for your outlet temperature, which is a converged solution for your iteration. Okay. Okay, I guess that's this problem. Is there any question? Yeah.
Yeah. All right. So whenever you get your answer the first time.
Yes.
So whenever you get your answer the first time, how do you so you get your properties at the average between your answer on the first time and the inlet temperature. Oh, and that's your new T bulk, I guess. Okay.
Yeah, because your lack of information to actually in the beginning to estimate the property, to determine the property, because you only have an inlet temperature, but you don't have an outlet temperature for the pipe, right? So it's your goal to calculate. So what you can do, you can start with 60 degree, or you can start with, actually the starting point is pretty arbitrary. It's not really arbitrary, but it's relative. If I were you, I will probably start from the average between 60 and the wall temperature 80. You see my point? I start with the average because now I don't have the outlet, but I have a wall temperature 80. I know my fluid temperature, average fluid temperature is less than 80, but it's greater than 60. Right? So now in the book, it said that I start from temperature 60, but it's really this step is to be determined. I can start with 70 because my wall temperature is 80, my inlet fluid temperature is 60. It will be in between 60 and 80 for the fluid. So why not I do an average of 70 first? I use 70 degree, I can determine kind of property. The second round will be also much better than the first round. Now you calculate a outlet temperature. I think it will be still around the 71.9-ish, okay? So maybe 72.05 maybe, okay? So then now you have an average temperature. Now you have an outlet temperature calculated based on the first try. So now you do the average, get a property that will better. Then will turn out to be 71.88 for the second round. So yeah.
The average temperature is basically to get better values from the chart, and then you can get a more accurate T bulk.
Yeah, that's your goal, right? You're an engineer, you want to have the most accurate calculation that you can. Okay, so but your lack of some of the conditions to do a best estimate at the beginning, because you should use the average of the inlet and outlet temperature to get the property. That's the proper way. Okay, you should use average inlet and outlet temperature. That's the average fluid temperature. Okay, you should use that, but you don't have it for this problem. The problem asks you to calculate the outlet temperature, so you don't have. So what can you do? You settle with some other temperature. It's okay. I'm going to do iterate. Okay, I'm pretty sure my first round is not that accurate. Okay, but actually it's not too bad. 71.98. Okay, it's not too bad, but it's not most accurate I can get. So let's try 60. That's what the book would do. But if I was the author, I would try 70 instead for the first try, because I have the information of the wall, okay, wall temperature, okay. So average of the inlet and the wall, maybe it's better than just use the inlet temperature, because in the fluid inside the pipe, it's higher than 60. I'm pretty sure it's higher than 60. And I'm sure it will be lower than 80. So I can do the average between them, these two, to start my estimation. Does that make sense?
Yeah, that makes sense.
Yeah. This class is unique, okay? It's not like other class you took, like fluids, like statics and dynamics. It seems like a very theoretical, you have the equation, you have the certain definite way to find the property. Here, it's more applied, very applied. Seems like it's in real time, like you're solving a real problem, and you don't have those informations. What do? You have a strategy to get the best answer you can, right? Did you see that? That's why I like this topic, It's kind of very applied and related to the work. Okay. I guess I'm out of time now. Any question? I can entertain one more question. It's 11:49 now. I want everybody, 21, all of you, fully understand this procedure. It's really not difficult, right? Do you agree? It's not difficult. Apply equations, but it's very tedious. It's easy to make a mistake during the process, okay? So that's why you get a good pay, right? To do the job. You have to make sure it works and it works correctly. Okay. Any more questions? So is that good? Okay. So next time we're gonna start the turbulent flow. I will introduce a couple more equations for you to do. Okay. So be prepared. Be prepared for the previous last Wednesday, last Friday, and today's class. I will give you a quiz after the break. So, okay. Okay, have a good break. Have a good Thanksgiving. Happy Thanksgiving. Happy holiday. Okay, see you next week.